Good morning. This is Dr. Dan Guerra from VerEvMed Studios in the inland/Pacific Northwest. Today, we're going to follow up on a lecture we did just about a week ago discussing the leukotriene-mediated inflammatory response and how it was regulated, indeed, by its receptors' level of phosphorylation, which was, I thought, a really beautiful description of how biology generates a three-dimensional grid of signaling that ultimately leads to trafficking of cells, the maturation of those cells in interaction with other cell types in the blood, and then ultimately an activation of other cell types generating indeed a very specific inflammatory response in situ in exactly where the tissue has been penetrated or stressed. It's a tremendous amount of chemical and physical information that is biochemical mediated response that can occur just by generating a gradient of one particular eicosanoid, that is an oxygenated fatty acid known as leukotriene B4. Today we're not going to, well, in a way, unfortunately, spend much time on lipids because, of course, leukotrienes are lipid mediators. But we are going to talk about the enzyme that synthesizes that LTB4, and you're going to find out that that enzyme has more than one function. And it's all related to disease, in particular the airway diseases, things like asthma and COPD. So let's go ahead and get started. All right. So we're going to talk about the leukotriene and matrix peptide events in airway inflammation disease. Remember, I talk about event ontologies in this series of lectures. We don't talk about substance ontologies. We talk about things that are happening in time. All right, so that's me. I'm Dr. Daniel John Guerra, and that is my particular email down there. You can contact me through that, and within 24 hours, I will get back to you. I come from VerEvMed. This is my company. And you can see our website and our individual in our specific email address that you can contact through that website. You can either get me through there or through my Gmail account. Remember what we do here. We're scientists verifying the scientific evidence, okay? And normally we talk about medical or biomedical sciences. However, we do a lot of work in physiology, in genetics, and also, of course, in various aspects of pathophysiology and pharmaceuticals. So it's a broad spanning aspect, and the company deals basically with clients who want to learn more about what the scientific literature is saying on a given topic. So this completely goes over the top of any of the popular press or any of the nutritional stores or anything that you might get from newspapers or periodicals. They're trying to sell you something. I go right to the scientific literature. I am indeed a scientist. I have a PhD in biochemistry. And what I do is I read the research for my clients and then vet the evidence that is in that research and discuss it at the level of verification, looking at the corpus of the other literature. And do that for each of my clients who have a specific question related to some scientific aspect they're interested in. Let's say it's nutrition. Let's say it's some kind of new supplement you want to be taking. Let's say it's a series of pharmaceuticals that you've been ordered to take from your physician. I work with the physician and with his patient or her patient so that we can get more at the science as far as the person, the client that is, wants to know. So that's what we do. And today, and these lectures that you see here, these video lectures I put up on YouTube, are basically just free calling cards, the kind of in-depth discussion that I will do with you as a client. Obviously, something that would be completely between my client and myself. And I wouldn't be discussing these things in the open forum. So this is just basically the kind of thing I do. I've been a lecturer, that is a professor for a very long time, of biochemistry and cell biology and biomedicine. And so the kind of lecture style I have is, of course, a lecture rather than having people come into the classroom having read something and just have an open discussion. That happens too in the real life classroom. And indeed, VerEvMed, we can do online actual discussions using Skype or using various other platforms so that we can have an interaction three-way with your physician or with someone else that's interested in knowing something about the science. So we have all different kinds of possible electronic means to have these discussions. Anyway, sorry for all that introduction, but I don't do it very often, and I was reminded I should do that. Here's the Facebook account that I use for VerEvMed. It has all the postings of all these lectures, video lectures on there. And it also has some philosophy because I tend to write a little bit of Western philosophy as well. And you'll also see pictures and silly things like that. That is the actual date today, 12th of September, 2018. And let's get started. All right. How we do this is I'm going to take a look at an individual paper that's been published very recently, and I'm going to dissect it, disambiguate it, and then verify the evidence and discuss it according to the other evidence that's out there, and also ultimately go through a dialectical understanding and then a diaeventological understanding of that data and evidence as it relates to the biological system. If you don't know about what those later significations mean, you will see soon how the distinction comes apart when we discuss it. The paper I'm going to talk about today primarily is from Science Translational Medicine, published the 22nd of August, so that's not quite a month ago. And there is the actual reference right there. So let's go through some of the introduction, just like the paper does. Inflammatory responses with supporting tissue remodeling occur during chronic lung disease. So you have inflammation and you also have tissue remodeling. Those are two biological paradigms that occur during the disease state. Lung disease is, of course, a major health concern and includes quite a variety of diseases, including the purely hereditary cystic fibrosis and a lot of acquired pathologies, including things like asthma, which itself is a large paradigmatic disease state, and chronic obstructive pulmonary disease, or COPD, which is, of course, can be fatal. Chronic inflammation may or may not drive airway remodeling. That's a key thing. And it can be important disease treatment strategies. So remember that even though you have inflammation and airway remodeling and chronic lung disease, they could be separated. Okay, that's the whole point of this paper, actually. The key metabolite, leukotriene B4, or LTB4, is generated intramembranously. That is, the reaction itself happens within the membrane, either the nuclear envelope or the plasma membrane, and sometimes associated with the ER. And the enzyme that synthesizes LTB4 is indeed leukotriene A4 hydrolase. It synthesizes it from phospholipase A2 mediated production of arachidonic acid. Arachidonic acid is omega-6 fatty acid, 20 carbons with 4 double bonds. That fatty acid is very common in the 2 position of glyceryl phospholipids found in membranes. It is a signaling molecule. The arachidonic acid is a precursor to signaling. It has a tremendous repertoire of literature about it. And remember that I'm telling you that that fatty acid is omega-6 and that you synthesize leukotrienes from it. Understand that there's also omega-3 fatty acids where the double bond is at only the 3 carbons away from the methyl terminus of the fatty acid. And when that happens, when the fatty acid has that kind of molecular geometry, the products of that pathway, that would be the lipoxygenase pathways. We're talking about lipoxygenase 5 here. What happens there is that often the products of the omega-3 leukotriene pathways will compete with the omega-6 series. And that's the whole background of omega-3 versus omega-6 fatty acids in potential mediation of disease states. Something I talked about many times before in VerEvMed lectures, and we will, of course, get back to because this is a pretty important topic. At any rate, let's get back to what we're here on today. Leukotriene A4 hydrolase and generates this leukotriene metabolite, and it works through the G protein coupled receptor BLT1 via a series of hierarchical phosphorylation events. Now, again, I went through this just last week, and it's in a nice, beautiful lecture that's published there, and there you see the link right there if you want to take a look at that lecture first, you get an idea of what leukotriene B4 is like and how it reacts with its receptor, etc., then I recommend you take a look at that. You don't need to, though, so let's move on. So there's a chemokine-like activity of LTB4. Now, what chemokines do is they are chemicals that are generated in the blood or in the lymphatic fluid. And what chemokines do is attract, right? They attract cells to a given location. That's what chemokines do. So there's a chemokine-like activity of LTB4. And what it does is facilitate leukocyte chemotaxis. Leukocytes are things like neutrophils and macrophages and eosinophils, right? So, or also known as white blood cells. And of course, leukocytes also include lymphocytes, which are T and B cells, and all the possible manifestations of those. Okay, such as plasma cells for B cells and natural killer cells, etc. So it facilitates leukocyte chemotaxis, movement to a location of stress or damaged tissue. And then it also induces degranulation. Degranulation just means that there are granules inside those cells, and basically those granules are really just high concentrations of enzymes, usually hydrolytic enzymes that are secreted by those cells, and those enzymes go on to attack, let's say, a bacterial or other pathogen invasion, or simply just try to control the potential for an infection, okay? And the degranulation of those enzymes also does a couple of other things, but we don't need to go into that for this talk. Anyways, all that is also in concert with subsequent T cell activation, and that all instantiates inflammation or the inflammatory response. It occurs both physiologically, that is, it happens under normal conditions, that is just repairing wound sites, but also within the pathophysiological state, including those characterized, yes, with chronic inflammatory disease, which is the topic of today. Now, another important point, they are all important, but the ones I've highlighted are super important. Pharmacotherapeutic blockade of the enzyme LTA4H, okay, using those inhibitors, have yet to fulfill their putative promise to rescue from chronic inflammatory disease. So drugs have been made to blockade or inhibit that enzyme because it's believed that enzyme controls that inflammatory response because it makes the LTB4. And the idea, very simple, of course, is, well, gee, if we make something that blocks that enzymatic activity, maybe we can prevent the overreaching of the immune response so that you can get rid of chronic inflammation. The point there is chronic, that adjective, because chronic inflammation is never a good thing. You want the inflammation to resolve and go away, right? Now, one inhibitor that's out there, J&J, 409, etc., has been used, and it has very potent pharmacodynamics. That means it does really inhibit the enzyme, right? It has pretty good pharmacokinetics, too. It gets passed through the body okay, it doesn't get degraded very quickly. It seems to have good potency. So that means it has efficacy, right? Nevertheless, it's failed clinically, in particular in a human bronchial allergen challenge model of asthma. So the question might be, why did it fail? Works, right? It destroys the activity of that enzyme. So something else must be going on. See? That's how biology often works. Like we think we understand something, we target it with something like, say, an inhibitor or a monoclonal antibody, and we say, well, let's see what happens in an animal model. First, we do it in cells. Yeah, everything worked okay in cells. Then we maybe move up to in the animal model, like a murine model. Yeah, it seems to work okay there. And then we try it with clinical trials, and wow, sometimes it just falls flat on its face. So why is that? Obviously, we've missed something. And what we've missed is that we're focused too sharply on just that particular reaction mechanism, and not all the other things biology very happily offers to physiological as well as pathophysiological conditions and paradigms. All right. So inflammatory airway diseases are associated with something called the extracellular matrix, or the ECM. These are gel and fibrous proteins that basically are the scaffolding and architecture for the assemblages of tissue-associated cells. So cells are embedded in this matrix, if you want to look at it that way. Okay, it's what the cells are bathed in, is the ECM, and that ECM again is just a bunch of protein structure, not just protein, because there's lipid there and carbohydrate there too. In fact, the proteins are glycoproteins. or lipoprotein, proteolipids. But at any rate, basically it's a proteinaceous matrix, the ECM is. And what that does then is create the environment for the cells to be embedded within a given tissue, say the lung. So it is the ECM where intracellular communication lays the foundation for development, homeostasis, and in fact, inflammation and tissue repair, right? Because that's where the communication network has to occur. The ECM is, of course, like everything in biology, prone to damage by, say, invading microorganisms, damage by UV radiation, like being out in the sun a lot, which is what I do, or just normal aging or senescence, right? The ECM degrades, just like every other thing that biology does. And that will require, when things are working correctly, rebuilding and maintenance. First detection of the lesion, then a rebuilding of that lesion, fixing it, and then maintaining that and preserving that back in its normal potent state. So any major ECM deterioration is kind of like breaching a highly interactive yet buffering demilitarized zone. If you look at it from a military allegorical perspective, which I never do, but I just came up with that one. I thought it was kind of a good one. At any rate, ECM destruction itself, when it's destroyed, is going to generate fragments, right? And those fragments can be antigenic. That means they can induce an immune response, you betcha. And they're also just naturally bioactive in one way or another. They do other things besides just elicit an immune response. And these molecular fragments from the matrix have a name, of course, because we love to name these things. And they are called matrikines. Matrikines, okay? So keep that in mind, the matrikine. So the particular matrikine called proline, glycine proline, or PGP, is a tripeptide, as you can see there, okay? And again, it comes from that tripeptide comes from that glycoprotein complex, which is a component of the ECM. So PGP can be proteolytically generated from ECM collagen, and it's no doubt that it comes from collagen because look at all that proline and glycine. Collagen is a super triple helix, and it has a lot of proline, and it has a lot of glycine, and also has some alanine, right? So that protein, when it is degraded, is going to have, no big surprise, a lot of proline and a lot of glycine. So that peptide fragment is something you would expect in collagen. So you get that peptide from sequential matrix metalloproteinases, or MMPs, which are another huge topic in biomedicine, something I've covered previously. Often MMPs, when they aren't working correctly or they overreact, are major players in invasive metastatic cancer. Okay, just if you want to look that up right away and see what I mean, you'll see there's a whole body of literature on it. There's another enzyme called prolyl endopeptidases, or trichars. There's two enzyme mechanisms required ultimately to make the PGP. Remember, this is a matrikine, and it's going to be a peptide fragment made from the matrix that's going to be involved in the disease. That's the point. That's what this little diagram shows you here. You've got these glycoproteins here. Some of them get hydrolyzed via the metalloproteinase. You make these limit peptides, right? Some peptide product from that metalloproteinase activity. And then ultimately the prolyl endopeptidase works on it and you make the PGP. Now the PGP has a couple of fates, okay? Let's take a look at them. It can generate an active aldehyde, and that nitrogen atom there can be acetylated. When it's acetylated with acetate from acetyl-CoA, it makes N-acetyl PGP. Now this in itself is a matrikine that has good strong function and potency. But okay, that particular product, because of everything else in biology, it can be degraded. It can be degraded by an enzyme called angiotensin converting enzyme. It's a very common ubiquitous enzyme, ACE it's called. In fact, that has a huge literature too, which I'm not going to get into. So you got PGP, which is a matrikine. You got its acetylated form, which also is a matrikine. And then you've got the degradation of the acetyl PGP to acetylproline plus glycine proline, the dipeptide. Or the PGP itself can be degraded by, look at this, gosh, the same enzyme that makes LTB4. So LTA4H, that enzyme, that hydrolase, which is normally shown, you open up any biochem textbook, including ones that I've published in, And you'll see, wow, that enzyme is responsible for leukotriene B4 biosynthesis. What's it doing degrading a peptide? Well, sorry to tell you folks, but if you haven't been totally inured in biochemistry, and I'm sure most of you haven't, you'll find out that just because an enzyme has a specific activity doesn't mean that's the only activity. Okay, so that means that enzyme might be necessary for converting ultimately an arachidonic acid hydroperoxy product from the lipoxygenase pathway, ultimately to say LTB4. But just as well, that enzyme might be necessary for an entirely different pathway. That's nothing to do with lipids. And this is a case in point. So many enzymes, which remember, of course, are the products of genes, right? The proteins are. Enzyme is a catalytic protein, have multiple functions in the cell. And how do we even know that? Because if we first isolated the enzyme from the cell, because we're looking at reaction pathways or metabolic pathways, we isolated the enzyme, maybe we isolated the gene, we know a lot about it, we know a lot about its mechanisms, etc., cofactors, its Km and Vmax, and all the other catalytic parameters. Guess what? We might have totally missed that enzyme has a totally different function. This is how this comes out. You make a drug, you're knocking out the activity of that enzyme, and what you find out is that, wow, not only did you decrease the amount of what you thought was the product, you did something else. Okay, so that's the point here. It's really kind of interesting. Anyways, this particular cartoon came from the European Respiratory Review. It's not the same paper we're looking at. So another thing I do in these VerEvMed lectures, of course, I'm building from all the other papers I'm reading, right? So I just want to make sure that I give credit whenever I use a diagram or a slide. Okay, so the matrikine PGP can be proteolytically generated, shown here. PGP can be subsequently degraded by, I'm just telling you, repeating what I said, by the extracellular leukotriene A4 hydrolase, right, to resolve inflammation, okay, because remember this is going to be involved in inflammation, okay, or the anacetylated form can be ultimately degraded via ACE, okay, and I want you to know that the N-acetyl PGP, this compound right here, which is naturally produced in the body, is a very potent neutrophil chemoattractant. Okay, good. Now, the PGP is a damage-associated molecular pattern, or known as DAMP. Okay, it senses, DAMPs normally sense and direct localized inflammation and repair processes. That's what DAMPs do. They're molecular signatures, and they're often actually generated from the degradation of bacterial cell walls, right? So you have DAMPs generated from bacterial cell walls. That generates an immune response because it's antigenic. And that's how the bacteria gets caught, trapped, and killed by things like macrophages, right? And the rest of the immune system. So let's take a look at what happens here in our lung disease, okay? So this is the airway passage, and this is the vasculature, okay? So respiratory infections can damage airway epithelium, shown here as one of the damaged ones. It's purple, and the others are nice and red, which means they're full of mitochondria and functioning correctly. The damage can be from UV radiation, or it can be from some other kind of nasty xenobiotic physical or chemical agent. It could be caused by microorganisms like bacteria. And it can even be caused by an auto-inflammatory or autoimmune response. Somehow, though, that lung epithelium, or cigarette smoke, that lung epithelium get damaged over time. Maybe it's caused because you live in an environment that has a lot of pollution in the air, for example. So respiratory infections can damage airway epithelium and activate cells to produce LTB4. Boom, right there. Okay. And the LTB4 in combination with other neutrophil chemoattractants, okay, like what? Like PGP, right, can drive neutrophil recruitment from the vasculature and into the tissue. This is the actual tissue, past the epithelia, the parenchymal tissue of the lung. Okay, this comes from European Respiratory Review, again, 2018 paper. Okay, now as neutrophils navigate through, this is all a dense gel and fiber ECM, and it's just showing you, like, if you blew it up, there's a lot of collagen in there. Okay, because so it makes up the gels and fibers inside ECM. You can make that PGP or the N-acetyl PGP. And that it's at the leading edge, okay, of this now neutrophil, okay? That allows the neutrophil to have directionality and persistence in the matrix. Now, what happens is it makes a lot of this tripeptide, and those tripeptides can act as breadcrumbs, right, In other words, they can drive, because of chemotaxis, because of a gradient of these compounds, these tripeptides, drive the neutrophil to move through, to plow through the ECM, causing what? More local damage. Yeah, but that's not the only thing it's supposed to be doing. So let's go through this. The tripeptide can act as breadcrumbs to guide other proximal neutrophils to the specific site. Site of what? Damage caused by, say, a microbe, right? Originally. Okay, the foundation, right, happened there. The baptism of this degradation pathway leads to the rest of the sequelae. That's what I'm saying. Okay, so they actually repair proximal airway epithelium. There, shown there is the wrench. I didn't do this. That comes from this paper. I don't know that I wouldn't have used a wrench, but probably not. I probably would have thought of something else, but it's kind of cool. To seal the breach, okay, putting it back together, sealing the breach. That's the remodeling, you see. And promotes neoangiogenesis, so rebuild that tissue to facilitate ultimately wound healing, because you just damaged something, now you have to repair it. So that's what PGP is supposed to do, right? It's involved in remodeling, which is a good thing. The problem is that chronic lung disease, you get too much remodeling, you get too much fibrous tissue formed. And that then causes vasoconstriction and difficulty in breathing, which is one of the final what? Representations of things like COPD and asthma. You see, so when this gets out of hand, it causes dysfunction. Like everything else, you have to have controlling mechanisms. Remember the controlling mechanisms here, this can get degraded, remember? You get degraded by ACE, it can get degraded by LTA4H. The same enzyme that initiated it can also destroy this chemoattractant. Right? Very clever, very cool, and that's how cells are. They're smart. So PGP, acetyl PGP, can ultimately contribute indirectly to their own degradation by promoting vascular permeability of, wow, look at this, the enzymes LTAH4 and ACE. Okay, it's like because it promotes vascular permeability, right? That's what these do, because they're involved in wound healing. They're involved in chemoattractant. There are peptides that are functioning there at the cell-cell interaction level. All right. So that resolves inflammation, though, and that's what you want. You want to remove this. You've made something very potent. You want to get rid of it, right? Just like the LTB4 can be degraded. We talked about that last talk. So can these DAMPs, these PGP, for example. Okay. Now, to better resolve the LTA4H PGP degradation pathway in chronic lung disease, what I just went through, it will be necessary to determine the controlling mechanisms involved in that biochemical, chemosensing, leukocyte-mediated inflammation and disease etiology. I love writing sentences like that. I don't know, because it's all right there. All right, now for example, the enzyme, right? The enzyme involved in leukotriene biosynthesis and also degradation of PGP can function as both pro-inflammatory and anti-inflammatory, thus reversing the pathology and hence an insight into the failure of why the inhibitors of the enzyme don't work, right? If you're knocking out the anti-inflammatory response, what do you get? If you negate anti-inflammatory, you get inflammatory, right? Or pro-inflammatory, right? That's how it works. Or at least you get neutralization. Neutralization, if you have a buildup of what is normally pro-inflammatory, still ultimately secretes and obtains as pro-inflammatory. Basic logic. So the current 2018 paper that we're looking at, right? This is Science Translational Medicine paper, the 2018 paper, August 22nd, reports on the dual functionality of that enzyme in defining the pathogenesis of, asthma. When these researchers delete LTA4H, they do it by doing a double knockout of it. The LTB4-driven inflammation does get removed, but an exacerbated airway hyperresponsiveness, which is part of the disease etiology of asthma, COPD, also as AHR, right? Hyperresponsiveness, airway hyperresponsiveness, owing to PGP accumulation, substitutes as the etiologic agent of the continuation of the chronic disease, even though you've knocked out that enzyme. So AHR is that cardinal feature of asthma, and of course, we know how to analyze it. One of the ways we analyze it is with a compound called methacholine. So in order for you to understand the paper, you have to know, in order to go to figure 1 in the paper, you have to know something about what methylcholine activity does. So let's take a look at this. This is called the methylcholine challenge test. It can be performed by your physician in his office or her office. It's also known as the bronchoprovocation test, and it's performed to evaluate how reactive or responsive, synonyms here, your lungs are to things in the environment, right? Okay, so what's going to be put in the environment? Methylcholine. So take a look at how this works, okay? We're looking at what's called the FEV1, okay? See here, FEV1. What is that? That's the amount of air you can forcefully exhale in 1 second, okay? Stands for forced expiratory volume in 1 second, okay? It's a small one there, right? The FVC, some of you physicians I'm sure are quite familiar with, is known as the maximum amount of air, and also exercise physiologists work with this. Maximum amount of air you can forcefully exhale. So that FVC actually stands for forced vital capacity. It's a different parameter. Let's take a look at this, the way this mechanism works to study whether or not a patient has asthma or is healthy. The asthmatic will have a decrease in the FEV1 as you add methylcholine at very small, low concentrations, sub-micromolar. Okay, so how does this work? Okay, again, you're evaluating whether or not you have asthma, okay? It can help your doctor evaluate symptoms suggestive of asthma, such as a cough, chest tightness, and shortness of breath, and help diagnose whether or not you have it. During the test, okay, you're in the doctor's office now, you'll be asked to inhale doses of methylcholine. Wow, okay. The drug can cause narrowing. In fact, it causes the narrowing of airway. What it does, it causes vasoconstriction. It's similar to what happens in asthma. Now, a breathing test will be repeated. That's the FEV1, okay, how much you can exhale in a second, okay? After each dose of methylcholine to measure the degree of narrowing of constriction of the airways. This test starts with a very small, sub-micromolar, only like 10 nanomolar level, very small amounts, very potent compound. And depending on your response, the dose will be increased until either you experience 20% drop. Here we went all the way to 50% drop. Holy cow. Or you reach a maximum dose with no change. And that's what happens in a healthy person. You see you plateau. See, you're getting some decrease in that VFV1, but it plateaus because you're healthy, right? This vasoconstriction is just showing you the underlying vasoconstriction induced by the methylcholine. You don't have any asthma. You don't have any thickening of the airway passages. You don't have any of that condition of remodeling that went overboard. You don't have any chronic disease. So you have to understand that's how you read this, okay? So this is a decrease, percent fall in the FEV1, okay? So this should look like this if you're healthy and like that if you're not. Rapid response to methylcholine because you already have a problem with your forced expiratory volume. Okay, adding this even just exacerbates it basically. Okay, now what they're going to show, okay, in this paper is that PGP acts as a neutrophil independent agent in promoting severe and indeed pathological epithelial remodeling in lung disease. The result itself, they claim, will account for a substantial amount of acetyl-PGP, which you find, guess where you find it? In the sputum of severe asthmatics. Now, see, that's how one of the ways we learn that this is an agent. What do you expire if you have asthma? What's in that sputum? Well, one of the things is acetyl-PGP. See how that works? So they're going to claim they're going to find this. Now, how will the results support the conclusion? Well, first of all, you have to look at the methods they used. I just showed you one. Now I'm going to give you the other major method in the whole paper. Very basic stuff, but really important physiological mechanistic responses. You have to know how the methods are generated and why the methods do or don't work for the given paper. You might have a very good hypothesis. The hypothesis looks good. Why does that enzyme, when you knock it out, why doesn't it repeal the chronic disease state? Okay, good. But what are your measurements? How do you determine whether or not what you are applying in terms of your research methods and then the readout you're going to get from it? How do you know whether or not you're actually looking at that particular disease state? Well, first thing I just showed you made sense. The FEV1 makes sense. If you look at that, you know that you have an asthmatic. It's also a good indicator whether or not you have a drug that's repealing it, right? Yeah. Okay, now here's part two. First of all, I'm making another note on experimental method in the clinical setting. Again, this is from a paper called, from a journal called from a paper, called bronchoalveolar lavage, that's BAL, for the evaluation of interstitial lung disease. And the paper asked the question, is it clinically useful? And those are the authors. And it was published in the European Respiratory Journal some 7 years ago. So I dug this paper out to make sure I understood what the method was they were using in the paper, you see, because I didn't know it until I looked at this. So now, normally you apply thoracic high-resolution computed tomography, HRCT, to clinical pulmonology, which is what would be applied medically for this condition. And HRCT has definitely revolutionized the diagnostic approach, looking at all human interstitial lung diseases like COPD, like asthma. Good. However, bronchoalveolar lavage, BAL, can also play a significant role in making accurate and, in fact, confident diagnosis if you happen to be the clinician. And you want to know what kind of ILD you have, right? Really important stuff. Now, when BAL is used in conjunction with HRCT, so both methods, nucleated immune cell patterns will provide intel for the diagnostic evaluation, and they'll lessen the need to proceed to more invasive, what you don't want to have to do, lung biopsy. Because lung biopsy often, it will require surgery. Most people don't want to say, yeah, I want to go get a lung biopsy to determine whether or not I have COPD or not. Wouldn't it be nice if you could just do the CT scan and maybe back it up by giving up a little bit of the alveolar lavage, right? Some of the fluid. Indeed, it would. So that's why these are basically relatively non-invasive methods to determine what kind of disease you have. So indeed, BAL can also identify confounding conditions because it's looking at what's inside that lavage, right? So you can determine whether or not you have an ongoing infection, right? A real-time ongoing infection. That's also important because an infection might just mean you have what? Influenza. You have the virus and you don't have asthma at all, see? Or, unfortunately, it could also mean you have malignancy, right? Lung disease of some kind that could be could involve some oncogenic events. So looking at what's inside that fluid, that lavage, will give you a lot more information maybe than just the HRCT. Okay, here we go. Finally, we can look at the first set of data. Now, I want you first to look at this. We were looking at that FEV, and I want you to make sure you understand that sometimes the curves are drawn differently, because it depends on what you're putting on the y-axis and the x-axis. Here we're looking at lung volume in liters, okay? We're looking at a patient with COPD, and we're looking at the increase in lung volume. And on the y-axis, we're looking at total airway resistance. This is a different measurement than that FEV. This is resistance. It's measured as, for example, centimeters of water per second per liter, okay? Reciprocal second per liter. And what that does basically is tell you how much resistance occurs through the airway passage, right? It's that kind of readout. Now, normally that by the way, that's called raw, R sub AW. In a healthy person is about 1.5 as an average. And it goes from 0.6 to 2.3 centimeters of water LS, okay? Which we're just showing you here. There's a healthy person there. As you increase lung volume, of course, you're getting a decrease in resistance because the lung volume is getting larger, see? But if you have the disease, right, if you have some kind of ILD, that number is going to be much higher. It's going to be greater than 10, okay? Now look here, look at these numbers. These are raws, okay? Now this isn't showing you a decrease because you don't have lung volume here. What do you have here? You have the methylcholine, okay? So it's a totally different parameter, but you remember if you add that, what are you doing? You're restricting. So rather than opening up the volume, you're restricting. So the curves are going to go in the other direction. Okay, you get it, right? All right. See, but you wouldn't have known that unless we went through this whole discussion of this, right? That's why I want you to understand what we do here at VerEvMed. We get you to where you really understand what it is is being tested on you and how to understand the data. All right. Now, basically what you see, I put these little red asterisks here. This is just a histogram of this data, by the way. And these are, you got to understand a little bit about what we're looking at here, of course. First of all, this figure is called augmented airway resistance. It means more airway resistance in a house dust mite treated mouse. Okay, so HDM can induce an asthmatic response. Okay, that's how you do it. It's a method to trigger it. Now, what is this LTA4H minus minus? That's a double knockout mouse. That's a gene. Otherwise, it would be capital LTA4H. Remember, what is that? That's the enzyme in leukotriene biosynthesis. That's the enzyme they're studying, right? Heck yeah. So they made a double knockout. I'm not going to go how they do that. I've talked about it in various other VerEvMed lectures, but basically we can ablate a gene. Double knockout means because you're a diploid organism, so it knocked out both copies of the gene. So you have a null at that locus. That enzyme's not there, at least in this system. So you treat them with something you know you're going to induce asthma. You don't have this enzyme at all. So not having this enzyme is kind of like mimicking if you took an inhibitor to it, you see? All right. You induce asthma. You don't have this enzyme. It's like you inhibited it. You still get airway resistance despite reduced airway inflammation. And that's what this data is going to show you. Holy smokes. So what we're looking at are wild type and the double knockout mouse. And they're administered, again, this house dust mite, or just basically phosphate buffered saline, right? And they give it intranasally to these mice. They gave it 3 times in 3 weeks. See, 3 intervals in 3 weeks. They really load up that HDM. They really want to give it a master shove into asthma, right? Asthmatic attack. Now, what you find here, take a look at this. Holy smokes. Really beautiful. Remember, though, if you don't have this enzyme, you don't make LTB4, and that's pro-inflammatory, leukotriene, also chemoattractant. You don't have that. Again, need more detail? Go back to my previous video lecture. I gave you the hyperlink to it. Or just remember what I said. And also, though, because this enzyme degrades PGP, you don't get the degradation. So this red arrow means it builds up. And what is that? That's a chemoattractant involved in remodeling. The remodeling, when it goes overboard, can cause airway resistance. And boy, golly, that's exactly what you see. The asterisk here shows you, okay, so these are the knockout with the house dust mite. You get higher levels, right? You get more of this resistance as you add more methylcholine because you're showing the response. It's a direct readout by not having that activity. So the reason you're getting that isn't because you didn't make LTB4. It's because you preserve the level of PGP. See, dual functionality. So there's more resistance when you double knockout, when you have a double knockout of LTA4H, and that suggests the augmented airway resistance asthmatic response to methylcholine. That's what you see. That's just showing you here histogram form. I see it's statistically significant. Between the wild type mouse and the double knockout mouse, you get a lot more of this resistance. Remember what the resistance is measuring, right? Resistance to airflow, right? Not a good thing. Asthma, right? Now, then they go on. The rest of this diagram shows you where we get airway resistance, decreasing doses of methylcholine was measured 24 hours after the final exposure. Okay, so what we're looking at here are the total number of cells. Okay, so we looked at all this. Now we're down here. What we want to say is that we're looking at what's in that lavage, that bronchoalveolar lavage, right? Well, there's cells that when you treat with the dust mite. So something's moving in there, something extravasating into there, okay? Yeah, because what you're doing, you're inducing the asthmatic response, so you're getting the movement of what? Leukocytes. Now look here, the wild type, when you add that, because you're inducing asthmatic response, actually has more of total cells in the BAL than the double knockout. You're getting less chemoattraction. And when you look at what kind of cells are there, the eosinophils, okay, which are again a part of the innate immune response. The eosinophils, along with IgE, are kind of like major players when you look at lung disease, okay? less in the double knockout, statistically significant, than in the wild type. And you get nothing happening when you just add PBS, of course. So that means that not having this enzyme means you get less of the leukocyte invasion. Leukocyte invasion involves inflammation. So it looks like you're getting augmented resistance, boom, up there, but you're getting less of the inflammatory response because you don't have inflammatory cells, leukocytes, and particularly eosinophils. And look here, you don't also have CD4 positive, right, monopositive T cells. Okay, you get like none of those if you knock that out. If you knocked out LTA4H, if you knock out that enzyme, you don't get any T cells because you're not getting any of the dendritic cells causing the mobilization and activation of T cells, right? So the acquired immune response isn't kicking in either. But remember, you're still getting resistance. You still get disease symptomology. Got it? And I know that there's a big scatter here, but again, it bulks around right here in the wild type, and it apparently is significant, much higher levels than what you get when you get double knockout. So when you get rid of that enzyme, you're not invoking the immune response if we're not invoking inflammation, yet you're getting augmented airway resistance. Just showing you that particularly a really potent pro-inflammatory cytokine generated from CD4 positive cells, T cells, is that interleukin 13. And look at this, you get a lot less of it produced when you get to double knockout. And that makes sense. You don't get much recruitment of T cells, you're not going to get much of the cytokine the T cell makes. Yeah. That's what the whole thing is telling you. And that was assessed by flow cytometry, all these different cell types. So, all right. Next. Now we're looking at Th2, that's T cell H2 effector cell type of T cells, and the cytokines it generates. And this is an acquired T cell response, part of chronic lung disease. Now the cytokines it makes, Th2 cells, that lineage, are IL-4, 5, and yeah, you just saw 13. In fact, those are pro-inflammatory cytokines. Those are secreted proteins from those cells. What do they drive? They drive inflammation, but they also drive remodeling. They also drive that airway hyper responsiveness we talked about, remember? And that's all what we see in the murine model of allergic airways disease. We have a murine model. We have a mouse model. That's what we're using. And these cytokines were increased in bronchoalveolar lavage fluid, BALF, right? And lung homogeneous or wild-type mice upon HDM exposure. Boom, you see here. There's more of it there, IL-4. There's more of it there, IL-5. There's more of the IL-13. We already saw that data, right? But what's going on with the double knockout? Not so much, even with the induction with the mouse mite. No. So you're not getting any of these pro-inflammatory cytokines made from T cells now. And we already kind of knew this because we were looking at the single positive CD4. Now we're looking at Th2 lineage, which is the more matured form of the T cells involved in inflammatory responses from the acquired immune system. Okay, what else is going on here? Similarly, concentrations of the eosinophil, right? That's back to the innate immune cell, leukocyte. These are lymphocytes. Chemoattractant Aotoxin 2 were reduced in the double knockout. See, less of that. Okay, what else? Mast cells, another innate immune cell, are increased in allergic airway disease. Yeah, you get all the immune cells moving in. Of course, not just one particular variety. But the concentration of mast cell protease 1, that's MCPT1, is much less when you do the double knockout. So you're not getting these mast cells moving in either. So there's no differentiation. There's no selection of what kind of leukocytes are moving in. You're just not getting any leukocytes moving in the airway passage, yet you have asthma, okay, as induced by the house dust mite. That's what they're showing you here. All right. Now, edematous airways tend to be narrower. Because they're narrower, whatever is going to be in that fluid, right? This is all fluid from the bronchoalveolar lavage, right? So you're going to increase the amount of whatever's normally in the fluid. What's in the fluid? Albumin. Albumin's everywhere, right? It's in all fluids in the body. So edematous airways tend to be narrow and prone to airway hyperresponsive behavior. That's the whole system we're looking at here. However, HDM administered double knockout mice, okay, demonstrated a marked reduction in albumin. See, look, boom. And finally, the HDM-specific serum immunoglobulin E is also reduced in the double knockout. And the only place where you see very little effect is in IgG, and that's because the B cell response isn't well characterized in this disease. So you wouldn't expect to have any differential effect when you are tinkering with the positive-negative selection, basically, of the etiology of the disease through the ablation of the double knockout of the enzyme responsible for the degradation of PGP, and of course, the biosynthesis of LTB4. So this is just making sure you're knocking down all the markers and make sure you understand what's going on. And what this basically is saying is, gee, there's no inflammatory response when you've got the double knockout. Now, I love biochemical pathways. Okay, so we get to do one. I'm sorry, I said it's going to be about lipids. Of course, you got to add something because it is about lipids. Now, recall from last time that hyperlink I gave you for that elegant talk I gave just a week ago. You've got arachidonic acid that's generated from the 2 position of a glycerophospholipid, such as, say, phosphatidylcholine or phosphatidylanosyl phosphate, that's embedded in the membrane. Phospholipase A2 is activated because of stress, some kind of response occurs, some kind of damage effect to the membrane and generates arachidonic acid, becomes a coethioester, and then gets acted upon by the 5-lipoxygenase pathway, right? It makes the hydroperoxy, and then it makes the hydroxy tetraenoic acid. I went through this pathway before. Now, when you start making leukotrienes, you say, well, wait a minute, there's 4 double bonds here. Yeah, but these are conjugated double bonds. So that's the triene you're talking about. And there's your epoxide and LTA4, and there's your the hydrolase basically opens up that bond. You see, you opened up that epoxide bond. And that's when you make this LTB4, which is ultimately resolves as a dihydroxy, so somewhat water soluble. Went through all this before. Now, beyond that, and we already know this is important in this disease, LTA4 can go through the glutathione transferase pathway. It can make peptidoleukotrienes. Basically, you're adding glutathione, the tri-peptide. Not the same tri-peptide we're talking about. Glutathione, totally different piece of work. Anyway, you make gamma glutamyl, you make the tri-peptide, the peptidoleukotriene here with all 3 amino acids. That's cysteine, glycine, glutamate. That is indeed, okay, that's what a glutathione is. Then there's a transpeptidase, which removes the glutamate, and now you have a dipeptide bound there to that sulfur free acid attribute from cysteine, right, to that carbon. And then there's one more enzyme called dipeptidase where you just make LTE3. LTC4, LTD4, LTE4. These are very potent vasoconstricting substances, some of the most vasoconstricting substances known to man. So they are going to decrease the size of that airway, and they are in fact involved in anaphylactic shock. In fact, you can die if you get high levels of the production of these, right? Very, very deadly. So this is what else can happen when you get a nasty episode of asthma. These compounds can be made. LTB4 can be made off from arachidonic acid. This is just showing you there are also things called lipoxins. And those go through the 15-lipoxygenase pathway, ultimately making this epoxy tetraene, and then resolving that, you make 2 lipoxys. Now, why am I showing all this? Well, yeah, of course, I know that lipids are the most significant biological compound. In fact, the most significant molecules on Earth, probably in the universe, wherever there's anything important in the universe, and not just dead space and hydrogen and helium. But I maybe digress a little bit, but not really. But the paper wants you to know about this a little bit, because dig this, of significance. Data in the supplementary figures, which I'm not going to go through because these papers have supplementary figures, and there's a lot of them here. They're all important, but I'm not going to show you the data. I'm just going to tell you what it says. Other mediators of inflammation, the lipoxins, and particularly LTE4, okay, common allergic pathways were reduced in the mice, due to the absence of LTB4. In other words, you don't get an increase in the lipoxins or LTB4 because you've ablated this reaction. You might think it could happen. In fact, that does happen. In other words, it jumps over. You make LTA4 because of 5 LOX, or 15 LOX picks up the arachidonic acid, or the 12 LOX. See, 3 different reactions, 15 lipoxygenase, 12 lipoxygenase, 12 or 15, and then this is the 5. But you can take LTL4 and you can make these peptidoleukotrienes, or you can make the lipoxins. These are all involved in disease, okay, and inflammation and an allergy. But they found out they didn't get any increase in it. So that's not what was happening. They had to clear that from the deck. In other words, now they're going back and saying maybe it's the peptide that's inducing that resistance. This is despite the double knockout presenting with an exacerbated AHR, remember the hyperresponsiveness. Although loss of the enzyme function can lead to an accumulation of LTA4, you guess, because that's the substrate for the reaction, right? And a shunt towards either lipoxins or the cysteinoleucotrienes, the most potent of the peptidoleucotrienes. See, terribly potent vasoconstrictive eicosanoids. These are all eicosanoids, 20 carbon oxygen fatty acids. No lipoxins or cysteinoleucotrienes were detectable in the bowel fluid. Now, I think we need to follow up on this. I'm interested to know why that didn't happen. Is that because you don't have these enzymes activated? Is PGP doing something to knock out the activity of those enzymes? Is an overload of LTA4 maybe inhibiting the reaction? I don't know. There's a lot that you need to ask. It might just be that you resolve this and remove LTA4 via maybe just hydrolysis to epoxide and then just complete removal of that cosanol, because there is a degradation pathway for LTA4. Maybe LTA4 is secreted away. But I think you need to go back and follow up on this. All right. Now, back to the data. Administration of the house dust mite results in elevation of BALF concentrations of PGP-generating enzymes. This is MMP9, right? That enzyme is the metalloproteinase. Matrix. So you get more of the enzyme that's actually you find in the lavage, right? You get it in the wild type, and you also get it in the double knockout. So you've got the enzyme, so that's good. You also get the prolyl endopeptidase. It's just a Western blot showing you that you get both when you add the house dust mite, you get more of the enzyme both in the double knockout. See, boom, strong band there, strong bands there in these mice. So that is on. So the PGP was increased, and that's good because look. However, look at what happens when you have the double knockout. You get a buildup of PGP. So you have it made, but you don't get it degraded. In the wild type, what happens is you get degradation, but in the double knockout, you don't. Why don't you get it? Why not? Because the double knockout's doing what? When you don't have the enzyme, you can't degrade the PGP. Remember? All right. So that's just looking at PGP degradation, just doing a mass spec of what you would get from this peptide fragmentation. You get a lot of fragmentation in the wild type. You don't get any when you get the double knockout, right? And indeed, when you do look at just how much free proline is there, right? This is just looking at absorbance of proline, doing extraction for proline in the spectrophotometer. Again, you get plenty of it when you have a wild type. You don't in the double knockout. See, boom, boom, boom. What is that saying? Okay, that no PGP or acetyl PGP was detectable in the wild type mouse. However, substantial concentrations was found in the double knockout due to an inability of the enzyme, because the enzyme's gone. So the inability of those animals are what I call TXKOs, double knockouts, to degrade the PGP. And that's what's shown in these exact figures that I just went through, CD and E. Now, the murine model of allergic airways disease is predominantly eosinophilic. Okay, something that just, it's what you see, it's how it's presented, with a minimal neutrophilic infiltrate. Since PGP is a neutrophil chemoattractant, you might say, well, maybe PGP increases in the HDM treated mice promoted neutrophilic asthma, the severe form of the disease. But that's not what you get. In other words, maybe the eosinophil thing is going wild because you remember getting all these cells, but when you knock it out, but look, not the case. You get the same amount of neutrophils, right? In the lung tissue, this was a biopsy, but these are mice, not humans. In the BAL, right? And you're also looking at an enzyme that is secreted from, right, after degranulation, right, from the neutrophil. So this enzyme MPO, which is the myeloperoxidase, which is one of the degranulation products. After the neutrophil shows up, it sends out this enzyme. No difference between the double knockout and the wild type when you hit them up with the HDM. Now, what does that mean? That means that this is not affecting the neutrophil chemotaxis, right? Not affecting that. So it's not like you're getting a big change in that. You're not getting any difference at all. So you can't say the double knockout disease is caused by a big buildup of neutrophil-mediated disease. That's not what's happening. Now, HDM-treated double knockout mice exhibited the augmented airway epithelial remodeling relative to the littermate control. So now we're doing staining. The wild type is here, and there's a double knockout. We use PBS. Yeah, this is using a stain called H&E, which is Hemolymph eosin Y, very common stain. The color gives nuclei is blue, and the cytoplasm is pink to red. Okay, so it's just a cellular stain. Most widely used for medical diagnosis. Now look what you see when you hit him with the dust mite. When you're looking at the double knockout, whoa, a lot more remodeling than you get with the wild type. A lot more remodeling. That's what that is. That's remodeling. More cells, right? And that is just a histogram showing you what's called epithelial height, right? So this is a stand-in for that tissue remodeling, the height of the epithelia. Okay, that's what this is. It's a surrogate, we call it. And this is just explaining to you these stains. So the data's here. I just went and got these papers because you have to know how these stains work and whether or not are they used in these lung diseases. Here's protocols from a 2017 paper. Yeah, they use this staining when they look at lung disease. Here is a paper from Diagnostic Pathology 2009. Yeah, they use the periodic acid shift staining, okay? And this is basically looking at glycoproteins. This is another very common stain. I want to make sure they use these stains because the paper is using them. This is data from the paper. This is from the literature. See, that's what we do at VerEvMed. We're vetting, right? We're verifying the evidence in the paper and saying, are these methods correct? It's always what I want to do when I read a paper. All right, so bronchoalveolar lavage, BAL, is a useful diagnostic tool in ILD. We know this. However, differential cell counts are often non-specific, and immunocytochemistry is time-consuming, so you can stain for glycoproteins using the periodic shift staining right here, the pass staining. Okay, basically what's this telling you, okay? Either way, when you get the double knockout, boom, boom, you're getting remodeling. You're getting remodeling. There's more glycoprotein in the double knockout. That's remodeling. See, there's more. Here's the histogram of this stain. More of that. And using this H&E staining, same thing. You're getting a little more. That means that you're getting more remodeling when you did the double knockout. That's really important. And that's what this slide says. HDM treated double knockout mice exhibit augmented airway epithelial remodeling. That's a etiologic representation of the disease. Okay. Now, what happens when you neutralize PGP? So now we're pretty sure this PGP is involved. When you neutralize it, you attenuate the heightened airway resistance. So look, here we go back to the resistance graph. And here what we've got are two different peptides we're adding. We have a control peptide, which is alanine, serine, alanine, which could have come from collagen, actually, because a lot of alanine. We don't expect it to act like what? The matrikine, because it's not a matrikine. It's just a tripeptide. So it's a control peptide. So what we say is PGP induces neutrophil migration in vivo, and that's a dose dependence, and it's involved in the development of emphysema-like changes in the airways. We already know this. The complementary peptide, RTR, arginine, threonine, arginine, that's the one that's going to be complementary to PGP, binds to PGP sequences. Remember, it acts like a damp and inhibits neutrophil infiltration. That's what you're seeing here. Okay, so when you add RTR, either to the wild type or to the double knockout, what you're getting is a decrease in what that resistance looks like. You're getting a decrease now in the resistance. Indeed, you see there's no difference now. There was before when you didn't ablate or neutralize the PGP. Now you are. There's no difference between the wild type and the double knockout. So resistance is the same, right? So what that means is that indeed, when you neutralize PGP, you get no effect of having that double knockout genotype, right? Because you've neutralized what you think is the etiologic agent, PGP. Indeed, that shows it. And then just going back to the staining, histograms of the staining, see these are same. There's no difference in these two, the wild type versus the double knockout. And of course, you don't expect anything really happening. You do see some increase when you add the control peptide because you're getting more, you see? So when you add the house dust mite in the double knockout, you do get more remodeling. Okay, we already know this, right? You already get more remodeling. But when you block the remodeling by blocking the PGP, you look just like the wild type, both in the H&E staining and in the PAS staining. Okay, so you get the bump. You do definitely, when you just add ASA, the control peptide, you're not inhibiting PGP. You get what we saw on the last slide. You get remodeling versus not remodeling. When you add the peptide that blocks the PGP, you neutralize it, their term, you get no increase in remodeling. Okay. By the way, well, I wanted to look at this whole thing and see whether or not it is used. In vivo RTR prevents both migration and activation of neutrophils induced by PGP, and RTR completely inhibits PGP-induced lung emphysema. I got that from a paper that's, 10 years old, FASEB journal. So I went back and I said, is RTR used? Because see, again, I'm always asking the question. Okay, they got this great Tri-Peptide. They say it's going to block PGP. Has it been talked about before? I'm vetting the literature. I'm verifying literature. Yeah, 10 years ago. And the literature is full. I just found the first paper. It's full of it. Okay. Almost done with data. Now we're saying the final question is, does epithelia, remodeling via PGP result from specific interactions of the peptide with just plain epithelial cells? Media itself, no effect. Now, the epithelial height is going to change if you've added, look at this, acetyl PGP, interleukin 13, which is what? Inflammatory cytokine, and both combined, okay? And indeed, what you find in the supernatant, right, of the animals that are the double knockout, okay, this is when you add these agents to generate, right, whether or not you get this product formed, right, you make that acetylated form, you get it every time you add. So look at this. Human bronchial epithelial cells are cultured with or without the acetyl PGP for 7 days. Analysis of the staining after 7 days showed that that's shown here, okay, that the acetylated PGP treatment resulted in an increase in epithelial height across the board, okay? All right, that's a surrogate, remember, for remodeling. In addition, the acetylated form enhanced mucus production. That's another what? It's another presentation of the disease. You get a lot of mucus formed in asthma, right? All right, and that's what you see here. There's more mucus. There's more mucus formed, right? All right, and that you find that with interleukin 13 because you know that that's pro-inflammatory. You know it's going to induce it too. So it's like a control, a positive control, right? All right, because it's a potent driver of goblet cell hyperplasia and mucus production. That's why they use it. Finally, the acetylated PGP causes an increase in epithelial. I'm not showing you this data. That's why I put this big thing here. In epithelial cell confluence, plus enhanced radial spreading, cellular motility, and loss of contact inhibition of locomotion. All of that, if that's what's doing to the epithelia, is phenocopying chronic lung disease. Therefore, this evidence, when you're using healthy tissue here, bronchial epithelial cells, you're getting a acetylated PGP directly altering those cells to act like they're picking up the disease, okay? So you're getting, again, this response of remodeling to the healthy tissue, and you're also getting more mucus formed. And that ultimately then is a test to see whether or not, now you might say, why are they using acetylated PGP? Well, remember the acetylated form isn't inhibited by any leftover enzyme. Wouldn't there be enzyme in this non-double knockout tissue? Yeah. This tissue is wild type. It's going to have plenty of the leukotriene hydrolase enzyme. So if you use BGP, you wouldn't get the effect. So they're using the acetylated form, you see, which is resistant to the hydrolase enzyme. That's why they used it. All right. Finally, the acetylated form of the peptide, acetyl PGP, is indeed elevated. These are two different cohorts. I don't even know why they tell you this, but one is in the UK and the other was in the USA. Now, what's interesting is that look at the UK, they looked at healthy. You don't get any of that in the sputum. That makes sense. But when you have a moderate to severe asthmatic population, cohort population in Britain, you get a tight clustering and definitely a significant increase in acetylated PGP, the etiologic agent for asthma. Okay? That's cool. Now, when you look at people in the US, now they're looking at people with some asthma, but not perfectly healthy. You get a little bit of bumping off of the zero. So you get a little bit maybe of that. But this is, again, non-severe or maybe even non-symptomatic asthma, or just people complaining because they have some hoarseness of throat. Maybe they just have something else going on. But that compared to severe asthma. Now, look what happens when you get severe asthma. You do get a lot of scatter. Okay. And that's not because US are just wilder, more radical people. I think it's because of severe asthma. So it's funny that they didn't have the same type of cohort exactly. But anyways, there's a bit of a spread here, which I don't like to see because it does suggest that there's a big variation in the amount of acetylated PGP in sputum. But this is only a one-shot deal. It does show you get a boatload of it. So it does appear to be made in severe asthmatics. All right. Finally, let's put this all together. This is my dialectic. Remember, dialectic is carried out many ways, but one is thesis, antithesis, synthesis. As a good existentialist, of course, we don't worry about the synthesis, but we do when we're talking about science, at least some kinds of discussion of science. Here we go. The thesis is enzymatic activity of the leukotriene A4 hydrolase activity, and the product of that is LTB4, is necessary for both the inflammatory remodeling aspects of allergic airways disease. Specific removal of LTB4 signaling blocked inflammation and indeed airway hyperresponsiveness in an inducing house dust mite mirroring model in the mouse. When they just say this in the mouse, remember they made a drug, right? So they made a drug, they inhibited that enzymatic activity. Remember that inhibitor I talked about at the very beginning of the talk. So they say, hey, we got a new drug. We got a new drug for asthmatics, maybe even for COPDs. So it worked fine in the mouse model with the HDM. So that thesis is that must be the etiologic agent. But the antithesis, we're doing a dialectic here. LTA4H is not necessary for allergic airways disease. Since the double knockout, same mouse model, double knockout, we got rid of both copies of the gene, right, of the enzyme, resulted in not in zero disease, which is what you might have hoped for, but rather in a more progressive and morbid hyperresponsive, hyperresistance type of airways disease, presenting with a reduction in mobilized leukocytes and pro-inflammatory cytokines. So you get less inflammation, but you get a bad disease. So elevated extracellular matrix dipeptide was what you found. So yeah, necessary. No, not necessary. So how do you synthesize these? Well, these aren't contradictory, right? They're not truly contradictions to one another, right? They're only contrary. To have a good dialectic, you can't really have two contradictory statements. Think of the square of opposition. I know all of you think about that whenever you think of anything anybody says. Good logical minds that you have. Now, the synthesis of these contraries is the following. Works fine. The activity of the enzyme includes both the synthesis of the hyperresponsive airways disease, LTB4, plus the removal of a second etiologic agent, PGP. Okay. So that enzyme removes PGP even while making LTB4. Hence, you get the difference between the contrariness between the thesis and the antithesis. Now you have synthesis. Beautiful dialectic. The conclusion then. The double knockout of the enzyme mirroring model presentation of an exacerbated AHR, that is again the readout of asthma, or ILD, was correlated with the accumulation of an extracellular matrix peptide fragment called PGP and an associated neutrophil independent agency, right? So independent of neutrophils, of this peptide to elicit a thickening of the airway. We saw that again and again with the staining of the epithelial layer and increased mucus production. We saw that, at least in one data set, leading to the occlusion of the airway and limitation of airflow. Remember the resistance data. There is a two-component system, therefore, we're concluding here, in airways disease, for example, in asthma, where inflammation is actually uncoupled from tissue remodeling. It tells us a lot now about what we might want to do with pharmaceutical production, right? With smart drug design. Oh yeah. These results may explain why enzyme inhibition pharmacotherapy is ineffective. May explain the reason. I put may in there. I don't think they say that because I'm worried still about what's going on with maybe the peptidoglycotrienes and lipoctins. Why didn't you flush into that pathway? So curious to me why they didn't see anything. Now, we go on, of course, because this is VerEvMed, and because I invented a new paradigm in science, and that's called Diaeventology. And you can hear about that and read about that and things I put together. In fact, I've recently submitted a paper on the Diaeventology of anxiety disorder, general anxiety disorder, which after review hopefully will come out online in the late fall or early 2019 winter. When it does, I will let you find out where that paper is, where I spend a lot of time talking about Diaeventology. But if you want to know more about Diaeventology, you need to just look at some of my previous lectures online. Anyway, the Diaeventology of airways disease. Now I'm applying my paradigm to this data in this paper. Genetic predisposition, that could involve different splice variants or different amounts or different slight variations in terms of SNPs of, say, the LTBH4 or the amount of peptide made because of the metalloproteinase activity, you see. And epigenetic modifications, we didn't talk about those, but I'm going to bring them up at the end here. Coupled with environmental damage like cigarette smoke or living in a high pollution environment or breathing in toxic fumes of some kind or other, or maybe a bacterial or a viral lung infection, right? Any of those things, that's environmental damage. Invoked an immune cascade of pro-inflammatory cytokines and chemokines that promoted the airway disease. Okay, we already know this, right? It's paradigm. But we're adding now, we're putting 3 planks together: genetics, immunoepigenetics, and environment. That's what Diaeventology does. Puts together the 3 to describe in 3 dimensions what's going on with the disease. I argue that diaeventological perspective is a significant way of looking at disease in biomedicine because it allows you to consider all the parameters. This paper, remember, went down this rabbit hole to find out why is this enzyme inhibitor not working. We made the double knockout and all that. Found out PGP is acting independently. But to add all that together is a diaeventological perspective, where the dia comes from what? The dialectic, right? And the event ontology, looking at things as events rather than substances through time, right? Ontologies. Okay. That is what's really there. Now, damage of the ECM in situ provides the platform for immediate response via proteolytic synthesis of the matrikine peptide PGP. Or peptides, that's when you add the acetylated form. That event as damps, that they event as damps. So I'm not saying they're substances because they're functioning as agents, right? They're agents, so they're events. They're not simply compound shows up and inert. You're talking about an event through time. So they event as damps. These matrikines event as damps, which are known as damage-associated molecular patterns, and bacterial fragments often do. And that's where they came from, by the way. That's where the result. And also, you can get this generated from your own cells, of course. They promote local inflammation and start tissue repair remodeling. That's what they normally do. Failure to feedback regulate the instantial, like showing up and doing something, that's what the instantial is, of the matrikines leads to overshooting the immune response, resulting in chronic lung disease. These matrikines invoke chemokine from endothelial cells, and they promote vascular permeability in the process and migration, proliferation, and tube formation, which we saw PGP did in the data of endothelial progenitor cells. Okay? Airway epithelial cells also express this receptor for the chemokine, which was necessary, right? Okay. Addition of the unacetylated form of the tripeptide metrikine to primary human bronchial epithelial cells promoted this chemokine receptor 1 or 2 dependent proliferation, radial spreading, and recapitulated the remodeling phenotype. So that was necessary to show, and they did. Recall that the acetylated form causes morphological changes, its data showed, indicative of the epithelial cellular motility and loss of contact inhibition of locomotion. These are all things necessary for the disease to progress and be chronic. PGP is normally degraded by local LTAH4 activity, but excessive production of the matricide allows for its acetylation to N-acetyl PGP, which is, of course, resistant to that degradation pathway. So you need ACE to degrade it. So the enzyme that's there, that showed up, it's instantiated, its instantial is there, it's an event ontology. It can't take care of the elevated levels of PGP because the PGP builds up so much it gets acetylated, and now the acetylated form is not a substrate for the hydrolase enzyme, which would normally degrade it. The only enzyme which would degrade it would be the ACE. And it has to show up as its own instantial by coming through the vasculature. So that could be a later, and that could be a less than sufficient amount of enzyme activity to ablate even the acetylated form. Yeah. Okay. So acetylation and methylation of histones plays a major role in the immunoepigenomics of airway disease. I didn't talk about this in this paper because it would have been another 12 slides. But indeed, if you acetylate or methylate the histones that are associated with this disease, looking at all those pro-inflammatory cytokines and growth factors and chemokines, you indeed find buried in there, beautifully orchestrated, an immunoepigenome. Okay. While not studied here, asthma drugs that are cystinyl leukotriene receptor antagonists, see, this is another reason why we have to go back and look at this, alter dendritic cells by epigenetically modulating cytokine expression, suppressing co-stimulatory molecule expression, and inhibiting the ability to initiate Th1, Th2 responses. So look at that. You get a drug that antagonizes the peptidoglycotrienes, right? And what you do is you decrease DC's ability to make cytokines because you get an epigenetic modification of the expression of the gene. Methylation and probably deacetylation going on to decrease cytokine production. So you don't get the co-stimulation, so you don't get the T cell response. Wow, that's amazing. And that's all in other papers. In fact, that little tidbit came from Pulmonary Pharmacological Therapy, 2016 paper. We'll go back and look at that sometime. Okay. So remember, again, take home message up here. PGP is normally degraded by that enzyme, but excessive production of the matricide allows for acetylation, which is resistant degradation and unleashes uncontrolled disease progression via unrestricted airway remodeling. Okay. That's the take home message in Diaeventology of this paper. This is adding more Diaevents to the ontology of the lung disease that we still need to consider, which weren't considered in this paper, but we will. So it's just a diagram kind of putting a few things together just so we can end on pictures rather than words. And of course, there are words too. So this is showing you the epigenetics of the system. Histone methyltransferases, such as the SETD7, this SUV39H1, no, that's not like a Humvee. That's a suppressor of variegation 3,9 homolog, which I hate the names of these genes. Again, blame the geneticists, not the biochemists. And then you have this other, this EZH2, which is enhancer of zesty homolog. Boy, that had to come from Drosophila research. Zesty, I think, is a Drosophila gene. Of course, a homolog to it. Anyways, those look like they are methyltransferases. And they'll kick on a methyl group to lysine 4 on histone 3, lysine 9 or lysine 27. Look what they do. These green arrows are showing turn this on. They get interaction of dendritic cells with naive TH cells, T helper cells, turn them into good T effector cells now, like this TH2 response. It starts secreting interleukin 4, interleukin 13, interleukin 9, interleukin 5, and even chemokines, right? These are all pro-inflammatory, right? So TH2 respond by making all these pro-inflammatory cytokines, leading to recruitment of eosinophils. See, eosinophils show up because this is the lung disease, right? IgE switching in B cells, you start making IgE, okay? You start making IgE from B cells. There are some B cells that show up, but they're not making IgG. Remember, they were making IgE. Okay, remember, yeah, they get that with the eosinophils also. Very common airway disease, IgE, not IgG. So B cells are showing up, but not the IgG response, the IgE response. And you're getting eosinophils. Okay. And other immune cells contributing to airway inflammation. Okay, so you're getting the whole thing. There's the neutrophils, there's the eosinophils, there's the mast cells, there's the B cells. Everybody shows up, right? All right. Now, IgE activated mast cells degranulate, okay? They degranulate, and that's when you get the production of more pro-inflammatory cytokines. Facilitates neutrophil, remember, it causes neutrophil infiltration. The Th17 cells making the IL-17 cause more neutrophils to show up. Now it becomes a neutrophil disease, right? You get more tissue remodeling because you're getting more PGP being made, and that results in severe chronic asthma. Okay, so that's what you've got here. You get smooth muscle hyperplasia. You're getting more of that remodeling you don't want. You're getting a full-blown immune response. This is all related to changes in the methylation pattern. So this is all involved in what? It's involved in the epigenetic control of this disease. I'm getting this all from the American Journal of Respiratory Cell and Molecular Biology paper published a few years ago in January 2016, 2.5 years ago. That paper is actually open and free online, and there is the link to it. Okay, and that's where this comes from in all this discussion. Now notice that HDACs, okay, SIRT1, small molecule activator of SIRT1, which is an HDAC, will block acetylation. Smoke will block acetylation. Any general deacetylation pathway blocks acetylation. But corticosteroids, okay, have a different phenomenological effect. Now look what happens here. If you block acetylation, right, if that doesn't happen, what you get is expression, okay? If you block deacetylation, you have acetylated histone, and that's going to cause the inflammation genes to be expressed. Oh my God, okay? So acetylation normally blocks this response too. So you don't get granulocyte macrophage stimulating factor, which is basically a pro-inflammatory cytokine. You don't get IL-17, which is a really potent pro-inflammatory cytokine, often associated with viral disease, but it shows up whenever you have a Th17 cell, which can be induced by things like vaccinations, by the way. So all of this occurs because you didn't inhibit it because you blocked deacetylation. See, I mean, you blocked acetylation. So what happens is if you don't get the deacetylation reaction, you have an acetylated histone, so you express all the pro-inflammatory genes. So you got methylation showing up as an epigenetic phenomenon, and you got acetylation showing up on the histones as well. And all of that opens up the chromatin, allows the expression of pro-inflammatory genes, and opens up this entire immune and indeed remodeling response. So that is just one slide showing you what we could spend an entire talk on. So we are done. Hope that you enjoyed our discussion of how, of course, leukotrienes are involved, and the enzymes involved in leukotriene metabolism are involved in the inflammatory lung diseases, ILDs, and indeed how manipulation and modulation of an enzyme that normally synthesizes LTB4, which is a pro-inflammatory leukotriene, actually then results in the loss of degradation of PGP, which is a tri-peptide matrix-formed modulator of tissue remodeling, which ultimately can also co-vary with disease. So we have to go back to the drawing board in our pharmaceutical companies and come up with better rational drugs, which will be able to look at both fronts, look at that tri-peptide pathway and look at that entire immune pathway I just looked at. Now, that's probably not going to solve everything, because it just showed you there's an entire epigenomic overarching activation, which again is a diaeventological paradigm, which is evoked in this disease. And all diseases ultimately have that. Okay, so ending now, my Facebook page, you're going to find this video on there real soon. There's me with the glasses, and there's my email address. Contact me. I'll be glad to talk to you via email and set you up as a client. We can get started right away like that, or you can go directly to our website. Sometimes it's easier just to contact me directly through my email, and I will respond, I promise, within 24 hours. Remember, we're VerEvMed. That's my company, along with my colleague, and this company is scientists verifying published evidence in medical biosciences. It's VerEvMed. Don't forget it, and please come and visit us, because if you do, you're going to get this kind of in-depth discussion directly just for what you're interested in. Okay. So all I have left to do now is say my normal sign off. And with sincerity, I say, bye for now.